suppose I can erase the hi. Well, hi everybody! What we're doing today is some physics force problems. So we're going to figure out, now that we've done some conceptual forces, what we need to do to actually solve force problems. So today's problem is Macie, interesting name, pulls a 40-kilogram rolling trunk by a strap angled at 30 degrees from the horizontal. She pulls with a force of 40 newtons, and there is a 30-newton rolling friction force acting on the trunk. What is the trunk's acceleration? All right, so I'm going to go through step by step on our problem-solving strategy so you can see in gory detail exactly what each step looks like. Our first step, just like with kinematics, draw a picture. So we've got a person, there's our person, and she's pulling a trunk. Well, let's put wheels on it, sure. And okay, we're moving in this direction. So what do we know? So our first step is draw a picture. Second step, figure out knowns and unknowns. We know the mass of the trunk is 40 kilograms. And Macie pulls with a force of 40 newtons. The angle of the pull is 30 degrees. And there's a 30-degree rolling friction. Okay, let's make that a friction force. Rolling friction force of 30 newtons acting on the trunk. And the question is, what is the trunk's acceleration? So our unknown, what we're looking for, is our acceleration. So there's step one, draw a picture. Step two, figure out your knowns and unknowns. Step three, choose the object of interest. Well, in this case, since I have the mass of the trunk and Macie's pulling on the trunk, I think I'm going to pick the trunk. So, trunk is the object of interest. Fourth step, draw a force diagram for the object of interest. And when you're drawing a force diagram, remember that you're only drawing the forces that the object of interest feels. So imagine you are the trunk. What do you feel? So I'm going to have a little box, and I'm going to put the forces on that the trunk feels. Easy force, force of gravity. We've got the earth pulling down on us with a force equal to mass times gravity. And we've got the pull of Macie going up at 30 degrees. Okay. What else do we have? We have rolling friction force of 30 newtons. Now the trunk is going that way. Friction, rolling friction, is one of those things that opposes the motion. So friction force is going to be backwards. Rolling friction, backwards. Is there anything else? Yep, we still have one more force. Remember that anytime you have something on a surface, normal force is there. So the trunk is on a surface, and so we have a normal force upwards. Is there anything else acting on the trunk? Well, imagine yourself as the trunk. We've got friction from the floor, the earth pulling down, Macie pulling up on you, and the floor supporting the trunk. I think we've got it all. Okay, so next step is choose a coordinate system aligned with the acceleration. And this is a key point. You really want it aligned with the acceleration because then the acceleration is only in either the x or the y direction. If you choose a different set of coordinate systems, a different set of axes, you might have acceleration in both the x and the y direction, and that makes your math way harder. It's still correct, it would still get you the right answer, but the math is much harder. So I'm going to choose a coordinate system based on my acceleration. Okay, let's go back to my picture. I think I'm going to accelerate in this direction. So if I have acceleration in that direction, I'm going to choose a coordinate system aligned with that. So acceleration is going to be in the x direction, and we've got the y direction perpendicular, got my coordinate system. Next step. Figure out if the forces are balanced or unbalanced in each of those directions. So I've got my horizontal x direction. Are the forces balanced or unbalanced? Well, I just said that there's acceleration in the x direction. So if there's acceleration, we must have unbalanced forces. So in the x direction, the forces are unbalanced because we have acceleration. In the y direction, what's going on in the y direction? Okay, so the y direction is this direction. Well, hopefully there's no movement in that direction. The trunk isn't flying up into the air or squishing down into the ground, so no motion, which means no acceleration, which means in the y direction the forces are balanced. No accel. All right, that's step 6. Step 7, set up a force table showing what the x and the y forces are in this case. Okay, I have 4 forces to keep track of, so let's put together a force table with 4 forces in it, and we're going to figure out what the x and the y components are for each of those 4 forces. So what are my 4 forces? And I'm going to do them in different colors so we can keep track. So we've got the normal force, we've got the force of the pull, and we've got a rolling friction force. What's our last one? mg. We've got our mg, earth pulling down on us. Okay, so for each of these 4 forces, we need to figure out if they're in the horizontal direction, the vertical direction, or both. So the normal force, well, that's pointing straight up. So the normal force has no left-right component, there's no horizontal component, and it's going in the upwards direction, so we have a positive normal force in the y direction. The pulling force, oh man, let's skip that one for now. Let's do the easy ones. The friction force, let's look at that friction force. It's going to the left. So is there any up-down component? Nope. The y component is 0. And we're going to the left, so we have a negative friction force. Okay, so all in the left direction. The weight force, okay, all going down. There's no left-right component, no horizontal component, and we are going downward, so we're in the negative y direction. And now we have the hard one. Okay, so that pulling force, it's both in the x and the y direction because we have a rightward component and we have an upward component. So we have to figure out what those are. So the pulling force, okay, I'm going to draw this triangle. The pulling force is the hypotenuse, the angle's there. Here's the x component, here's the y component. So the x component, this is the side adjacent to the angle. If you remember your SOHCAHTOA, which one has adjacent in it? Well, so that's opposite. Cosine is adjacent over hypotenuse. The cosine is adjacent over hypotenuse. Those are the 2 sides I'm dealing with. So this is the cosine component. And it's going to the right, so it's going to be positive. So positive pulling force times the cosine of our angle. The y component here, and this is opposite, so SOHCAHTOA, sine is opposite over hypotenuse. We have the sine component here, and it's going upwards, so I know it's a positive. Positive pulling force times the sine of my angle. All right, so I've got all my forces. I've got them all figured out if they're in the horizontal direction or the vertical direction. Now, what's my next step? Well, use Newton's second law. Newton's second law tells us that the sum of the forces, or the net force, has to equal mass times acceleration. So we're going to do that in both directions. We're going to do it in the horizontal direction and the vertical direction. So we have to do some erasing, and while we do that, I'm going to remind you that when there is no acceleration, that means that we have to have balanced forces and our acceleration is 0. So that was the horizontal direction was unbalanced. The vertical direction was balanced. So let's do Newton's second law in both directions. The sum of the forces, or the net force, in the x direction equals mass times acceleration in the x direction. Sum the forces, or the net force. That just means add up all the forces. Add up all the forces in the x direction. Okay, so 0, I can ignore that one. I have a positive pulling force times the cosine of theta minus my rolling friction force, and that equals mass times acceleration. The x direction was the direction with the acceleration. Now in the y direction, so here's one equation, In the y direction, F net in the y direction equals mass times acceleration in the y direction. Well, in this direction, we said there was no acceleration. Everything has to be balanced. All the forces have to add up to 0. So what do we have? Add them up. We've got 3 this time. So a positive normal, a positive pole sine theta, and a negative mg. Those forces all have to add up to 0. So we have 2 equations here. They both come from Newton's second law. This is Newton's second law in the horizontal direction. This is Newton's second law in the vertical direction. We want to know what our acceleration is. So which direction has what we care about? Well, clearly that one. So I'm going to look at the horizontal direction. We want to know what the acceleration is. Do we know the mass of our object? Yep. Do we know the rolling friction of our object? We do. Do we know the angle? Yeah. Do we know the pulling force? Yeah. We don't even have to do the vertical direction. We can actually solve this problem entirely in the horizontal direction. So this, while it's absolutely true, the physics is good, we don't need it in this case. We can solve this problem entirely with the x direction. So we've got everything but acceleration. We can figure out what it is. So the pulling force times the cosine of theta, theta was 30, minus the rolling friction force. Okay, and be careful. This was in newtons. This is a force. This isn't the coefficient of friction. So this is the total frictional force. So we can just put 30 in here because that is the force. We got it all. We know the mass, which is 40. And we're going to end up with acceleration. Look at that. Everything but acceleration. So in this case, we do our math and we get an acceleration of 0.12 meters per second squared. Okay, is that reasonable? So let's start out by asking, is it reasonable? Well, something that's free falling has an acceleration of 9.8 meters per second squared. I wouldn't expect that somebody running with a suitcase behind them would accelerate that fast. So yeah, it should be something less. And you don't really accelerate very fast when you're running with a big, heavy 40 kilograms. That's 88 pounds. That's pretty heavy to tug along behind you. So I would not expect a very large acceleration. I think that this acceleration is a reasonable number. So is it reasonable? Yes. Did we answer the question? Well, we were looking for the acceleration, so we did answer the question. Units, yeah, I didn't put the units in, but if I looked at the units, they would work out as well. I think we've got it. So that one is pretty straightforward. Now there's a second part to this question that asks us what is the normal force on the trunk. We spent half of a class period talking about the normal force. It's not always equal to the weight. So remember, it's not always equal to the weight. The normal force varies depending upon the situation. So for this problem, we need to figure out what the normal force is. Well, look at that equation right there. We know what the normal force is. I'm guessing we can figure it out straight from that equation. Do we know everything but n? Let's take a look. So we're looking for the normal force. We know the pull. We know the angle. We know the mass. And we know the value of the acceleration due to gravity. Easy peasy. So in this case, we can do the normal force. I'm going to bring this term over to the other side. Bring this term over to the other side. So that negative mg becomes a positive mg. This positive term subtracted off, so pulling force times the sine of theta. And I know everything. So the normal force equals the mass, 40 times 9.8 minus the pulling force, 40 again, times the sine of theta, sine of 30 degrees, and I've got it. So I can figure out what my normal force is. So 40 times 10, that's about 400. 40 times a half, 20. So this is going to be around 380. If I do the math, I get a normal force of 372 newtons. which is totally reasonable. It's not the full weight of the trunk, because the full weight of the trunk would be 40 kilograms times 9.8, which would be about 400 newtons. The strap that we've got here is pulling up a little bit, and so it's reducing the amount of force the floor has to push up on the trunk with, because we're helping out the floor. The floor doesn't have to do as much work because we're pulling up on the trunk a little bit. Not a lot, because it's not a huge difference, but yeah, a little bit. So have we answered the question? Normal force? Yeah. What is the normal force? We have it. The units will work out if you do the units. And is it reasonable? Well, if the weight of the thing is about 40 times 10, 400, then a normal force of 372 is totally reasonable. They're in the same range. If we got 3,000, it would be wrong. We'd know we had it wrong. If we got 3, we'd know it was wrong. So I'm pretty sure it is reasonable. We've answered all the questions. We've followed our steps, and we're done with this problem. So, good job.